So, good morning again. So now, today we're gonna solve exercise. We have only one page, so that's why I'm gonna show you one exercise, and it will be about yielding bending moment. You already had the idea about elastic behavior of reinforced concrete sections, beams, and you know already the difference between inelastic behavior and elastic. Our exercise will be in the elastic region. So our exercise is to find the maximum bending yielding moment of the section, okay, of the beam. So we need to find how much of the bending moment the certain section can resist before the steel bottom rebar will yield. Okay, yield means it will reach its yielding capacity, which is given in the Eurocode. Let's say for steel, for A500 steel, the yield strength is 500 megapascals. It means then bending moment will cause the beam to bend such that the stress in the rebar will exceed the 500 megapascals. So it will yield. Okay? So this is the basic idea of the yielding bending moment. Now we have a section which is very similar to the last exercises that we did. Here we have, I will note it as a D2 prime, and I have from top fiber to the bottom reinforcement D1. This is AS2, and this one is AS1. Now, if we have positive bending moment, bottom rebars will yield. If we have negative bending moment, top rebars will be yielded. So it's clear, right? So section characteristics, we have B 300 millimeters, we have H 500, we have diameter of the stirrup, which is VW, is 8 millimeters. Then we have top reinforcement is 2 P14, which means 2 rebars of 14 diameter. Then we have bottom reinforcement AS1, 4 20 rebars. Then we have concrete class, which is C, C30. Now I'm going to write some characteristics, some parameters that are taken into account for the safety of the structure. So this is gamma C. For the concrete, we use 1.5. Then we have for the steel 1.15. Then we have Young modulus of steel, which is also given 200 gigapascals. So we suppose that we already know the geometric center of the section, and it is the same with the previous exercises, which was 200 YG0 244 millimeters. It is derived by taking into account the homogenized moment of area, homogenized moment of inertia, and the first order moment of area. So this is derived from the homogenization, and it was explained in the previous lessons. So now we know all the characteristics of the section. So one more thing to add here is that we have axial force equal to minus 200 kilonewtons. So axial force is not zero. Our axial force is minus 200 kilonewtons. So our beam is in compression. So axial force is applied to the principal axis of the section, which means it coincides with the YG0. Okay? If it will not coincide, it means you will have double bending. So it will cause biaxial bending. Now we will find Now I'm going to find AS1, which is the area of the bottom reinforcement. So it is equal to 4 diameter 20 rebars, which will be 4 multiplied by 3.14 multiplied by 10. So it's 10 squared actually, because PR squared. Then we have 1,256 millimeters squared for the bottom reinforcement, area of the bottom reinforcement. Now, area of the top reinforcement is, we have two 14 diameter rebars. Then it will be equal to 2 multiplied by 3.14 multiplied by 7 squared. So it will be 308 millimeters squared. Now let's find D1 and D2 prime. Okay, distance from the top fiber to the bottom reinforcement and to the top reinforcement. So D1 will be equal from top fiber to the bottom reinforcement. It means H minus C plus cover plus area of the, diameter of the stirrup. So it will use VW, and plus half of the diameter of bottom rebar. E1 divided by 2. So it will be equal to, well, we have 500 minus C was 35 minus 8 and plus 8 and the plus we have E1 is 20 is 10. So it will be 447 millimeters. So D2 prime is distance from top fiber to the top reinforcement, to the center of top reinforcement. So this is C plus PW and plus P2 over 2. Am I right? So we have 35 plus 8 plus 7, which is 50 millimeters. Now, once we know all the characteristics of the section, our goal is to find the yielding bending moment. So yielding bending moment is found by applying the forces coming from two rebars, top and bottom rebars, and from the concrete, compressed area of the concrete. So it means we need to find three forces that are coming from the concrete, from the bottom rebar, and from the top rebar. So yielding is happening in the bottom rebar because we have positive yielding bending moment we're trying to find. Okay? So it means if it's in the bottom reinforcement, we will have sigma at the bottom reinforcement will be equal to the FYD. So this is the critical point where we should start. It means the yielding, the bottom reinforcement is being yielded. So the maximum stress on the bottom reinforcement will be equal to the FYD, which is FYK divided by 1.15. So 1.15 is the safety factor for the steel, okay, for the rebars. By dividing the yielding strength of the rebar, characteristic yielding strength of the rebar, I'm finding design yield strength of rebar, of the bottom reinforcement. So this will be equal. So we have FIK of the rebar type is so let me check our steel grade, because I think I didn't write here the steel grade. What is the steel grade? Well, steel grade, we have here, we have, I missed FYK, which is 450 megapascals. So our steel grade is 450. In Uzbekistan, in the local codes, we have A400, which would be close to this one. We have A400 and we have A500. So you can check, you can take between them. So FYK is 450. So now I will divide 450 by 1.50. And it will be equal 391 megapascals. So stress in the bottom rebar is equal to 391 megapascals. Why? Because bottom rebar is being yielded. Is it clear? If you have questions? Because we're trying to find positive yielding bending moment. If you want to find negative yielding bending moment, then you assume that top rebars are being yielded. This is assumption, but this is correct. I mean, let's say we will assume the same for the top rebar, but in a real case, top rebar will not be yielded. I will explain it just now, okay? So we found the stress for the bottom rebar. Now, I'm going to find the force at the bottom rebar, Fs1. Force at the bottom rebar will be equal to the stress, S1, multiplied by the area of the S1, which is area of the bottom rebar. So we have 391 megapascals multiplied by AS1, which is 266 millimeters squared. So force in the bottom rebar we have 441 kilonewtons. Is it clear? We derive it from the concept that bottom rebar is being yielded. So now let's assume for the process itself, how to solve this exercise is iterative process. So we need to do same process again and again until we get error less than 1%. At the end, I will show how to calculate the error. Okay. So if the error will be more than 1%, then we will change some data. So data that will be changed after the error more than 1% is the neutral axis. So now I'm going to find neutral axis, because this is like iterative process based on trial and error. So neutral axis. Now So imagine this is your section. So you have neutral axis. This is the top fiber of concrete, and C is the force coming from the concrete. So let's assume it's compressive force, C, here. Then we have also force coming from the top rebar, which is Fs2, right? And now we have bottom rebar, which is force is directed opposite.
It's inside of the thing.
Well, this is the stress-strain relationship, because we have linear low, I mean we are in an elastic region. This line will be linear, okay? Stress will change linearly. So the basically it is derived from this one. This is sigma concrete. Here we have sigma S2. Here we have sigma S1. Is it clear? Well, this is the diagram of the pressure, diagram of the sigma stress. So, if you have your section like this, incorrect. This is your section. Okay, this is neutral axis, YC. So if it's neutral axis, so it will be same here, YC. So your neutral axis is somewhere located here. So this part of the concrete is compressed. So this part is tensed. So that's why diagram is linearly changing on the opposite side. So the maximum tensile force is coming to the bottom rebar. Actually, this comes to the bottom rebar. Okay? It should be somewhere like this. Is it clear? So concrete, I'm not considering concrete because concrete has very low tensile strength. So that's why we are not taking into account the concrete. So concrete is contributing to the only compressive force, so it will contribute to the bending moment, only compressive force of concrete. Do the equilibrium for our section, for the forces, then we have NED equal to C plus Fs1 minus Fs2. Is it clear? Our axial force, which is external axial force, which was given at the beginning of in the description of the exercise, was equal to 200 kilonewtons, right? So axial force should be equal to the internal forces. Okay, sum of internal forces, which means we have three, well, let's say materials that is contributing to the resistance of the section, which is top rebar, bottom rebar, and the concrete itself. But the concrete will have contribution only compressed part. Tensed part will not have. So compressed part is equal to the YC. We don't know YC. So idea is to find a YC, which is neutral axis. So in order to find neutral axis, we are doing this inequality. Clear? Why? Now you will understand. So, we know how to find Fs1. We already found Fs1. Right? So this one, we know this one. For Fs2, we are assuming that it is also being yielded. We are assuming. It is not necessarily correct, but we are assuming it's being yielded. Then we have concrete. But concrete we don't know yet. C is equal 0.5 B YC CD or FCD. Doesn't matter. Sigma is CD and FCD is the same. This is the design compressive strength of concrete, sigma CD. You can also write FCD instead of FCD. Well, this value, these three terms, they give us the force in the concrete. Is it clear why these three terms giving the force? So it's clear because you have stress multiplied by the area, D multiplied by YC. This is B. This is the sigma CD is the design compressive strength of concrete. Design compressive strength of concrete. So these are the data that we have. Our concrete class is C3035.
And the value will be provided, right?
Yeah, well, you have the class, concrete class. From here, you need to find design compressive strength of concrete. You know the safety factor, which is 1.5. So design compressive strength of concrete is equal FCK divided by 1. Let's say gamma C. Is it clear? So it is just a design value. So concept of the compressive strength is the same with the characteristic one. Characteristic, you have to just divide by 1.5, which is safety factor. So in reality, you can just imagine that you are decreasing the value of concrete, the resistance of concrete, because you want to be on a safe side. Okay? So we decrease it, this characteristic strength of concrete by gamma C, which is 1.5. So the value will be equal to 30 divided by 1.5, and it is 20 megapascals. Is it correct? Okay. Now you know what does it mean. This it gives us force from the concrete. These three terms. So this 0.5 is assumed. Is the assumption that only half of the area of this compressive part is giving us the force, compressive force. So now we know all three terms of this equation. So let's write this. We have NED equal to 0.5 multiplied by B multiplied by YC multiplied by sigma CD. Then we have plus F. Let me write in FYD multiplied by AS1. Then we have FYD multiplied AS2. So from here we just find YC. So if you find YC, it will be equal minus FYD multiplied AS1 minus FYD AS2 then we have minus n divided by 0.5 b sigma cd. Yeah. So now, what is the value? Let me put some numbers. 391. This is fs1. This is fs2. This is n, and this is c. You can calculate them separately and write the equation. It doesn't matter. Then the only thing that you have to do is to find yc. So yc.
In the first row, is it AS1? Second
Yes, it's AS1. Thank you. So now we have 391 multiplied by AS2, which is 308. Then we have 200 newtons. Because we are using megapascal, I just converted from kilonewtons to newtons. About this one, right? Okay, now it was my mistake, so it should be plus.
Yeah,
Because we have minus here.
yeah, when we take it from this side to another, we will have minus.
Yes. Here we have minus, that's why plus. Yeah. Minus 190 millimeters. So we have YC, which is equal to minus 100 millimeters. Now, once we know the YC neutral axis, we are able to find the forces at the top rebar. Is it clear how we're gonna find? We will use just a linear relationship between stress and strain curve. Okay, so this is our YC. Okay, let me write. Okay, let's leave it like this. Here we have top rebar, which has two. We have is epsilon c, epsilon s1. Is it clear? I wrote it just in terms of strain, not stress. You can replace them because you have a linear relationship between them.
Because it's between stress and strain?
Yes. So now, the first thing that I have to do is to find epsilon s1. So now you see, I have epsilon s2, epsilon s1. But at the beginning, I told you that we are assuming top rebar to be yielded also. If it will be yielded, it would be same with this one. But it is not same actually. So I'm putting different epsilon s1 and epsilon s2. So now we're gonna find the stress at the top rebar. So epsilon s1 is equal sigma divided by E. Yes. So this is just a stress strain law, you already know it. We know sigma S1, right? 391 megapascal. Then we divide it by 200,000 megapascal. So epsilon S1 will be Do you have?
1.9, 1, yeah.
1 point.
95 times 10 to the power minus 1.
Okay. Let me write 96. E minus 3. This is the strain. So now we know the strain at the bottom rebar. Because we know just because it is yielded. Now we need to find strain at the top rebar. So you can just write from a mathematical point of view, you have two triangles and you can take the ratio of 190 to epsilon S2 is equal to this distance, which is,
500 minus 105.
no, this is D1 minus 190. Because this is at the rebar, okay? This is the center of bottom rebar. So now we do 190 over epsilon. Well, 190 is to find epsilon C, which is strain at the top fiber of concrete. If you want to find for epsilon S2, it will be less than 190. So now let me find first for the concrete. It will be 190 divided by epsilon C is equal D1 minus 190 divided by epsilon S1. Because we want to find epsilon C strain at the concrete at the top and strain at the top rebar. We don't know what is the strain. So by knowing the strain, we're able to find stress.
The relation of the ratio.
This is, do you know the equation of curvature? Curvature is a slope. No, not that one. Curvature, the meaning of the curvature is the slope angle, slope. So it means curvature x for your section, it will be equal to 190 divided by epsilon c. So you can write same curvature for the bottom part, because you have linear relationship. So at the end you can derive this equation. Or you can use just geometric properties of similar triangles that you have same angles. From the then you can write this equation. So now let's find epsilon c, which is equal b1 minus 190 divided by epsilon s1. Oh, sorry.
190 times epsilon S1.
Yes. Epsilon s1 divided by d1 minus 190.
3.7 times the power minus 4.
3.7
7 times the power minus E minus 4.
e minus 4. So please note that this will be minus because you have compression. Let's find epsilon s2. So epsilon s2, it will be yc minus d2 prime divided by epsilon s2 equal to d1 minus 90 divided by epsilon s1. So the same theory applied here, but I'm going to find the epsilon s2, which is strain at the top rebar. Is it clear? Now epsilon s2 is equal to yc minus d2 prime
Times S. Epsilon S1.
times epsilon s1 divided by d1 minus 190. Please put here instead of YC, just 190. So it would be 190 minus 50. We have 190 minus 50 multiplied by epsilon S1, which is 1.96 e minus 3 divided by d1, which was 470. Can you repeat? 447 minus 190. So the value
0, 100,106. Like it will be 1.1 multiplied by 10 to the power 3.
1.1 10 in power 3. So now we have the strain. You have different?
1.065. 06 which will be 1.06.
Okay. It doesn't matter, we can take this one. Now we need to find the forces coming from these three elements again. Okay, we are trying to find forces now. So now we have C1, which is equal to P2, B, YC. Please, I would like to highlight the point that our 0.5, if you remember, we had 0.5, is changed to beta 1. So this is the how it should be in the reality. Okay, you ask it. What is the? In the reality, we should take which value we should take. How to find? So first was assumption that beta 1 was equal to 0.5. Yeah, but it was just assumption to find YC.
No, like it will be given, or we should just take from.
Yes, you should know this. You can do different assumptions. You can assume that YC is equal to 100 millimeters, just by yourself.
Why?
Okay, minus 100 millimeters.
No, why?
Because by doing this, if you don't know the YC, you cannot solve the equation. You cannot find the bending moments and the forces coming from rebars and the concrete. Okay, if you know the YC, you can find the forces. Then at the end, you will sum up them. And you
check
can,
is it correct or no?
yes, then you will check is it correct or no.
And then if it's not correct, I again should substitute some value for YC and do all calculations again.
Yes, but the point is you will not just substitute. The next step will not be the next step will be YC will be calculated YC initial, your first YC, and the plus the value that should be added to YC. So it will be, you will change your YC based on the error you have. Okay? So only the first step is assumption. So now you have beta 1 coefficient here. And beta 1 coefficient is taken from the Eurocode, but it's not given directly by the Eurocode or any other code. So it is derived from the equation of stress-strain law again for the concrete. For the compressed part of the concrete, it is derived by the integrating the stress-strain law. Okay? So I will show at the end from the Eurocode from which equation it's coming from. So now you can just remember that beta 1 is equal epsilon c 6 minus epsilon c divided by 12. So epsilon c is equal 100, 1000 multiplied epsilon c. I mean, you know this. So you just multiply it by 1000. So here you have minus. Okay? Now you have 1.44 multiplied 1000.
Understand. We should have 10 to the power of minus 3.
Yes. So we will have minus 1 plus 1.44 because we have minus 1000. So now epsilon c is a minus.
Now we got 1.44.
No, it's in compression. Concrete is in compression. It is minus. Epsilon c is in compression. The previous value was also with the plus. This one is also plus. But we are taking minus because concrete is in compression. And because I'm not writing these equations, I've explained it already, that I didn't write here in terms of YC, in terms of coordinate system by taking into account the coordinate system. So that's why I have plus value. So it means here this value is compressed, this part is compression, right? This part is tension. So that's why epsilon c, everything in this part will be minus. So now we have 1 point. No, this is the equation itself.
It's given already.
Yeah, it's given, already given. I will share with you the description of this. So now we have epsilon c and beta 1 will be equal. What is your value? 0.55, okay? Let's say 55. Now once we know the beta 1, we can find the C1. You can also write C, C1, it doesn't matter. So it's the force coming from the concrete. So now we know the B1, beta 1. We can write 0.55 multiplied by B, which is 300. Then we have minus 190. Then we have sigma CD, right? 20. So how much we have? The value equal minus 627 kilonewtons. Now let me find, you already know FS1, right? FS1 was equal to sigma C, FCD times the area of S1. So the value was 491 kilonewtons. This is not changed. Since the beginning of the exercise, it's not changed because we already know that there is a yielding at the bottom rebar. But now FS2 will change. FS2 will be equal sigma S2 multiplied by AS2. This is not FCD like it was at the beginning. This is now sigma S2. So sigma S2 is equal epsilon S2 multiplied by E. What was our epsilon S2?
Epsilon S2.
Yes. Minus.
1.1.
Please note that it's also minus.
No, it was.
Yeah, but
YC, if we
yeah, it's in the compressed part.
1.1 multiplied by 10 to the power of minus 3.
minus 3 plus 200,000 megapascals. So what value you would have? Could you please? We will have 200 multiplied 1.1, which is 200.
220.
220. Let me check. Okay. 220 multiplied. Okay, 220 megapascal, right? Am I right?
Minus V.
Oh yeah, it's minus because it's compressed. Now I can find FS2, which will be minus 220 multiplied AS2. AS2 is 308. So please tell me the number.
It means 67,700.
So this one we have megapascal. This one is millimeter squared, newtons. We will have in newtons. How much you said? 67.
760. 700.
It's point you mean?
No. 67.
Okay, okay.
760. Без запятых.
So this will be 67.7
Kilonewtons.
kilonewtons. Minus. Now we have all three forces. Now we sum them. Okay? Let's sum them up. NRD. NRD means resistance axial force. Your section is resisting this axial force. Okay? Resisting axial force, NRD. Resisting RD, D is design, resisting design axial force. So now it will be sum of three forces, which is minus 627 kilonewtons plus FS1, which is 491 plus, but we have minus, that's why minus 67 minus 7 kilonewtons.
Formula 2 minus ide. Plus o minus mi?
Sorry, can you repeat?
The formula it was minus F S2.
Minus FS2.
So
Which formula?
which you give and E
I mean, neutral axis.
Было C плюс F1
minus
F.
F okay.
No, that one. Look. So we already have actually. We already have here the minus.
Yeah.
So the concept is the same. I put there minus. I didn't know the value of the axial force, but I put minus because I knew that it was
Negative.
negative. Because it was in compression. That's why I put negative. Minus.
But in the real time it will be plus, but we will get minus, so we put minus for the formula, am I right?
Let me check it. Let me check.
Минус 203. 86.
One more.
So here I'm putting minus. So that's the reason. The reason is because I'm considering it as a compressed part, and if I would plus it, I cannot put plus because instead of F by D, I'm putting positive value. Okay, you understand why? Because for the sigma CD, which is stress on the top rebar, I'm assuming that it is yielded. Okay, but it is yielded in a compression. So when I'm assuming that it's yielded, I'm taking the stress as a positive, sigma YD.
Plus we wrote and ED. We wrote because plus.
You mean this one?
No, on the second line. Plus and et should be.
Yeah. It was plus, yes. Again, see. So the idea, what I'm trying to tell you is that now when I'm trying to find NRG, my sigma is minus. Okay? My sigma is minus. But here my sigma is plus. So that's why I'm putting minus, because I know that it's compressed. See, my sigma cannot be, as you told me, I can put here plus. But then I would have to put here not plus FID, but minus FID. Because it's compressed. Okay? So it's the most important thing that you should keep in mind that it is compressed. When it's compressed, it's minus. So at the end of the exercise, you can check your results. Let's say you cannot have positive value for the top steel bar. If your bending moment is positive, your steel bars at the top should be negative. But again, there are some conditions that you have to consider. There are, maybe Professor Bertagnoli will explain to you in theory that there are 5 different cases that your neutral axis may be out of section. I will show you. In our case, our neutral axis is within the section, inside our section. But there are cases where neutral axis is here. I mean, your section is all tensed. You will not have a compressed part. Okay? It is also possible. There are 5 different fields that in a real case you have to take into account. Different cases. All compressed, maybe your neutral axis will be here. All compressed, all tensed, you have neutral axis within the section, out of section. Okay, there are 5 different fields. You can, maybe I will explain them, but as it's practice lesson, I feel like it's better to solve exercises, but this is theory. So now we have
minus 203.76.
minus 203.76
kilonewtons.
minus 200.
3.
3. Okay, I will
3.76.
correct it. Point
76.
7. So in my calculation, I have 202. That's okay.
1 kilonewton.
Yeah.
Почти
Now-
100 килограмм.
No, I mean, we will check the error. I think it doesn't make any big difference. The difference will be very small.
Having speed at least.
So the error
Nothing.
is equal to NED, which is acting external axial force, minus NRD divided by C, right? C. This is the error. So now we have 200 kilonewtons acting. It's actually minus 200. Then we have NRD, which is also minus. So we will have plus here. How much was NRD?
3.7.
203.7 kilonewtons. Divided by
Minus
C is
627.
637. So please tell me what is the value in percentage. You can tell.
So it's
0.5%. Correct?
59.
6 maybe, okay.
Dash.
So now, if the error is less than 1%, it means you can take this the already applied value of neutral axis. It means the values in your calculations are correct. Okay, let me finish. We didn't finish yet. Our goal was to find yielding bending moment. We didn't find the bending moment. We found the forces.
That's not by the YC.
Yeah, basically that's correct. We should find yielding bending moment around neutral axis. It means we should have to multiply by the lever arm for each forces. So yielding bending moment around neutral axis. Let me C multiplied by YC 1 minus. So now we again have beta 2. Beta 2, let me show you. This is the idea of beta 2. You know that Fs1 is a concentrated force, right? Because it's coming from the repulse. You know also Fs2 is also concentrated, Fs2. But force coming from the concrete is not concentrated, it's distributed. And you don't know if it's uniformly distributed or not. At the first assumption, we assumed that it's uniformly distributed. Now we are looking for the real case, and it is not real uniformly distributed. That's why we have to find this distance. Okay. If you know this distance, this is YC, right? We want to find the bending moment around neutral axis, around YC. In order to find bending moment coming from the concrete, we have to multiply the lever arm coming from, this is B. B multiplied by the C for the concrete, right? Is it clear? No? You want to find bending moment. For the Fs1, you know that this distance, right? Lever arm, which is equal to d1 minus yc. So if you multiply Fs1 to d1 minus yc, you will get bending moment coming from Fs1, from bottom steel. You know also top steel because you know the location. But now you don't know the where exactly the point load is coming from the concrete, because concrete is distributed load. I've showed here this is your concrete, right? You don't know from which point concrete will create bending moment around neutral axis. You don't know its center, which gives the force, which contributes to the bending moment of the section. So that's why, in order to find that point, we need B, right? B we multiply by C. So B, in this case, A will be equal to beta 2 multiplied by YC. This is the idea. Beta 2 is given by the textbooks for the Eurocode. Eurocode, it doesn't give directly the values of the beta 2, I mean the equation of the beta 2, and also beta 1.
A minus AC.
No, this is beta 2. Yes, 8 minus EC.
Divided by 4 times 6 minus CC.
Yes, that's correct. Beta 2 is equal 8 minus epsilon c divided by 4, 6 minus epsilon c. What time? It's already finished, right? Let me finish. So now I will write for the mx. So if you substitute, you will have 76 kilonewton.
EC will put the same
Meter.
value as for the B1?
EC.
Yes. It's the same as for B1?
Yeah, it's the same. You have to multiply by 1000 minus 1000.
Okay.
Then we have, let me write bending moment for the bottom rebar and top rebar. We have FYD multiplied by AS1. Then we have lever arm, which is D1 minus YC plus sigma S2 multiplied by AS2. Then we have lever arm, which is D2 prime plus YC. Is it correct?
Could you move to the previous slide?
So now you will get 135 kilonewton meter. So yielding bending moment around neutral axis will be equal to M concrete plus moment due to steel. And it's equal to 76 plus 135, 212 kilonewton. Concrete we calculated in the previous slide. This one is for concrete. Right.
Professor, CX still budget.
Just a moment. Okay.
No, MCX. Is it for still bar?
MC is for concrete, MS is for steel. For top and bottom, they are already summed. So, you have questions you can ask. I can explain.